we will discuss the concept of limits, including the four basic operations: addition, subtraction, multiplication, and division. First, we will define the concept of a limit. Let f be a real-valued function, which simply means that its function values are real numbers. Later on, we will introduce vector-valued functions, whose function values are vectors. Since those are more complex, we will discuss them in detail later. For now, let us return to the concept of the limit of a real-valued function. As shown on the screen, its notation indicates that as the variable x approaches a real number c, the function value f, x, approaches a real number L. Let's work through a simple example. Let's find the limit of the function x squared minus 2x minus 8 divided by x minus 4 as the variable x approaches 4. First, we factor the numerator into x plus 2 times x minus 4. At this point, we can cancel out the factor x minus 4. This simplifies our problem to evaluating the limit of x plus 2. Since we are considering the limit as the variable x approaches 4, we can simply substitute 4 into the function x plus 2 to get the final limit of 6. Next, we will introduce the concept of one-sided limits. First, let's recall our previous discussion about the limit of a function as the variable x approaches a real number c. Here, the variable x approaching c actually implies two different concepts. The first concept is that the variable x can approach the real number c from the left. This means that x stays to the left of c as it gradually moves closer and approaches c. Simply put, x is always less than c while approaching it. The limit obtained in this case is called the left-hand limit, and its mathematical notation is written as c minus. For example, when c equals 4, x approaching 4 minus means that x is always less than 4 while approaching 4, such as taking the function value when x equals 3.99999. By the same token, the second concept is what we call the right-hand limit. This is when the variable x approaches the real number c from the right. Simply put, x is always greater than c as it gradually moves closer and approaches c. In this case, the mathematical notation is written as c+. For example, the right-hand limit as the variable x approaches the real number 4 means we're looking at the function value as x stays always greater than 4 while approaching 4, such as taking the function value when x equals 4.00001. This example calculates the limit of the reciprocal of x minus 2 as the variable x approaches 2. Obviously, as x approaches 2, the denominator approaches 0, so the reciprocal goes to infinity. In this case, we must consider the left-hand and right-hand limits separately. First, when looking at the left-hand limit, that is, as x approaches 2 minus, we must consider x staying always less than 2 as it gradually moves closer and approaches 2. Since x is always less than 2, x minus 2 will be negative, which means the limit will be negative infinity. On the other hand, when looking at the right-hand limit, as x approaches 2 plus, we must consider x staying always greater than 2 as it gradually moves closer and approaches 2. Since x is always greater than 2, x minus 2 will be positive, so the limit will be positive infinity. This example clearly demonstrates that the left-hand and right-hand limits are not equal. This theorem states that the two-sided limit exists if and only if the left-hand and right-hand limits are equal. Conversely, if the two-sided limit exists, then the left-hand and right-hand limits must be equal. We will go over the proof later. Consider a function which is the absolute value of x divided by x, where x cannot be 0. This function can be rewritten as a piecewise function by considering the cases where x is greater than 0 and x is less than 0 separately. When considering x greater than 0, the absolute value of x simply becomes x, so we can just remove the absolute value bars. In this case, the function, the absolute value of x divided by x, becomes x divided by x, which equals 1. On the other hand, when considering x less than 0, to remove the absolute value bars, the absolute value of x becomes negative x. In this case, the function becomes negative x divided by x, which equals negative 1. This gives us the piecewise function, as shown on the screen. Next, we can calculate the limit as the variable x approaches 0. Let's find its left-hand and right-hand limits separately. First, for the left-hand limit, that is, considering 0 minus, when x is always less than 0, the function value is negative 1, so the left-hand limit is negative 1. By the same token, we can see that its right-hand limit is positive 1. According to the previous theorem, since the left-hand and right-hand limits are not equal, the limit of this absolute value function does not exist. Continuing with the previous example, for the same absolute value function, let's consider the limit as the variable x approaches a real number c, where c is assumed to be greater than 0. When considering the right-hand limit, that is, as x approaches c+, the absolute value of x still becomes x. Therefore, the right-hand limit is still 1. When considering the left-hand limit, as x approaches c-, even though x must be less than c, because c is positive and x can get arbitrarily close to c, x is still positive. Thus, we can simply remove the absolute value bars, meaning the left-hand limit is also 1. In other words, we find that both the left-hand and right-hand limits are equal to 1. Consequently, the theorem tells us that the limit of this absolute value function exists, and its value is 1. Next, let's consider the limit of the absolute value function when c is less than 0. Following the same principle, because c is less than 0, x will always be negative, regardless of whether x approaches c from the left, meaning x is less than c, or from the right, meaning x is greater than c. This means the absolute value of x becomes negative x. Therefore, by the same token, both the left-hand and right-hand limits are equal to negative 1. Consequently, the theorem tells us that the limit of this absolute value function exists, and its value is negative 1. Consider this discontinuous function. Obviously, this function is discontinuous at x equals 2. When we consider the limit as the variable x approaches 2, it does not mean that x must equal 2. Rather, the function only needs to be defined in the neighborhood of the real number 2. Therefore, when calculating the left-hand and right-hand limits, we consider the function where x does not equal 2, which is 3x minus 1. So, to find the values of the left-hand and right-hand limits, we can simply substitute x equals 2 into the function 3x minus 1, which gives us a limit of 5. Since both the left-hand and right-hand limits are equal to 5, the theorem tells us that the limit of this function exists, and its value is 5. Consider this piecewise function. As you can see from the screen, the function value is undefined at x equals 1. However, we can still ask for the limit as the variable x approaches 1. As mentioned in the previous example, the function only needs to be defined in the neighborhood of the real number 1. Therefore, for the left-hand limit as x approaches 1, we consider the function where x is less than 1, which is 1 minus x squared. To find the value of this left-hand limit, we can simply substitute x equals 1 into the function 1 minus x squared, which gives us a left-hand limit of 0. By the same token, for the right-hand limit, we consider the function where x is greater than 1, which is 2x. Substituting x equals 1 directly into the function 2x gives us a right-hand limit of 2. Since the left-hand and right-hand limits are not equal, the theorem states that the limit does not exist.